All right, so about waves, I want to tell you that waves are basically disturbances that carry energy. Now, that would be the simplest definition. A wave can be of two types. Wave can be electromagnetic. It can also be mechanical. For electromagnetic, I just want to tell you kids that it is all are transverse. Number two, all are transverse. Number two, they do not require a medium, can basically move through vacuum. Also, the speed of them in air or vacuum is about 3.0 times 10 raised to power 8 meters per second. That's about these. Then some of the examples of these are like gamma, light, X-ray, etc. So there's 7 of these. But then we also have the mechanical waves. So mechanical waves can be transverse or longitudinal. They are mechanical, so they require a medium, and also they cannot travel through in vacuum. Some of the common examples of these are like water, seismic, sound, etc. So you can write this down. Interesting, huh? Hmm. Okay, kids. Now let's go to the next and check out the rest. So for all right, let me. All right. Now we're gonna go to the transverse waves. For transverse wave, the definition is that these are waves that transfer energy perpendicular to wave oscillations, which basically means that the oscillations are going to be up and down, and the energy is being transferred perpendicular to that. Some of the common examples of these are water, light, seismic, S waves. When I say S waves, that basically means secondary waves. Oh, I already wrote it. Okay, so you write it here. No problem. All right. Then you have longitudinal waves. For longitudinal waves, you got to remember these are waves that transfer energy parallel to wave oscillations. Now, for these, you got to remember the oscillations are back and forth, and energy is also being transferred parallel to it. Some of the examples: sound, slinky spring, and seismic P waves. P waves means the primary component of it. Seismic means the earthquake ones. So if you don't know, that's what they are. Is it clear, kids? Any questions, please let me know. Now, in these waves, you would generally find crests and troughs, which are the bottom points. In these waves, you will find compressions, and these would be rarefactions. So spaced out ones are rarefactions, the closed ones are compressions. So you can add that as well, and later on we'll have a look at them again. All right, kids. Done. Should I go forward, please? Right. So I'm gonna then do this one. So you will have two different representations of these waves. You will have displacement and distance here, or you will have time here with displacement. Obviously, these are crests, as I've told you. These are troughs. Even sound is, kind of displayed like that, so that's fine. Crests, trough, and trough. Now, the first thing you'd like to find in any of these waves would be wavelength. That would be the distance between two successive points in phase. Now, this word in phase, I'm going to explain it a bit. But for now, just remember that the symbol for this is lambda, SI units of meters, and this is a scalar quantity. So if you go from crest to crest in distance wave, it will give you lambda. You could also go from trough to trough, that would be a lambda. Or you can just cover up one whole crest and one whole trough, that would also be lambda. The same distances you can try as well. Then, kids, we have amplitude, which is the maximum displacement of a wave from mean position. Mean position is this middle line. So the symbol for this is capital A. SI units are meters, and do remember, this is very important, that this is a vector quantity. So you can find amplitude by going from the mean position to the crest or to the bottom trough like that. That would give you amplitude. Fair enough. Then comes the time period. For time period, it is the time taken to produce one complete wave. The symbol for this is capital T. SI units for time period seconds, and it is a scalar quantity. So you can find time period on the time axis, but it's the same way as the lambda, between crest to crest, between trough to trough, or one whole crest and one whole trough together. Like that. Is it clear, kids? Any questions? Please let me know. So these are all IG stuff. I hope you guys are remembering that. Okay. All right, kids. Now comes displacement. And for displacement, we just need to remember that it could be distance in a specified specific direction from its mean position. The symbol for displacement, generally the examiner is going to use X or Y, and it is the SI units are meters, and it is a vector quantity. Remember that. So generally what they do is whenever they're asking you just displacement, so it'll give you like X here or maybe Y here. So it's not amplitude because that's not the maximum, but it could be any displacement on the wave. Finally, we have frequency, and about frequency, we can write it is the number of waves produced in a second. So the symbol for frequency is this italic F. SI units are hertz, H3, or simply second minus 1. Same thing. Again, this is just a count, so it has to be scalar. And the connection between time period and frequency is given by frequency equals to 1 over time period, like that. All right, kids, any questions? Please let me know. Okay, kids. Now, I hope everybody understands this. Should I go forward, please? Okay. Then you have wave speed. For wave speed, you guys need to remember that speed of a wave basically depends on the same formula that we've learned before. It's distance over time. Since the distance is the lambda now, and the time is the time period, so you can write it like this. And frequency is 1 upon time period, so you can replace the time period here, 1 over time period frequency. That will lead you to f lambda. It's a simple derivation here. Obviously, the SI units of this would be meters per second, and it is a scalar quantity, just like that. So thankfully, we're pretty much done with the IG part here. All right, kids. Why is distance the wavelength? Because wavelength is the distance between 2 points. Now, the length of a wave is lambda, and when that length is created, it causes, like, it takes t amount of time. The time period is, that's why it's t there. Get it? Very good. Very good. Who's unable to join? Wait, I missed that. Acha. Okay. Now, kids, moving forward to last IG thing, and that would be pressure and time graph. Now, I just want to tell you, pressure and time graph is created for sound waves, basically. And how it is created, please listen to this. Oh, write down this. So you have compressions, and then you have rarefactions. Okay, I give them a lot of space. Then compressions again. Then rarefactions and compressions again. So this will be compression, rarefaction, rarefaction, compression. So when you're basically drawing a wave for this, for pressure, just remember this important point. Pressure with respect to distance or time, it doesn't matter. So at the center of compression, right here, you will find the highest pressure. At the center of rarefaction, you will find the lowest pressure. Highest at compression, lowest at rarefaction. Highest, lowest, highest. So the wave would look like, okay, that's so good. The wave would look like this with respect to pressure. So just writing down for you, this is positive, this is negative. So highest pressure will be at compression center, and lowest pressure will be at the rarefaction center. Now, this question that you see right here is interesting question. Basically, it says a sound wave has a frequency of 2500 and speed. Could you guys help me find the um, wavelength for that? Yeah, I'm saying at the center of compression because particles are like pressing each other, you'll have highest pressure. Rarefaction means the particles are going away from that, so you will have lowest pressure and so on. Get it? Now, can you guys please help me find the frequent speed, please? Let's do that. It's C. Okay. Right, kids. All right. Fair enough. Anybody else have a different idea? There's a different idea actually about it. C. Right. Hajra, you should also come up with an answer. Yeah, Furqan and Shazib. You left. Actually, Alamin, you also. I don't know. I don't agree with them. If you have a different answer, you can put that forward. Could be B. Yeah, that works. Now you guys need to find the speed, no? So speed, sorry, wavelength. So speed is 1500, frequency is 2500 times lambda. Lambda does indeed come as this, but remember, when it comes to sound waves, the distance between a compression to a compression is a lambda, and a distance between a rarefaction to rarefaction is also a lambda. Now, in this particular question, it says, what is the shortest distance from a point of maximum pressure to a point of minimum pressure? Obviously, the minimum pressure will be here at the rarefaction and this one here, which means that this distance that you're looking at is not lambda. In fact, it is half lambda. So half of this 0.60 is going to be 0.30. Understood, kids? Everybody's clear about it? Very, very nice. Very, very nice. Hajra, is it clear to you? Fatma, Fiza, Asma? Okay, good. Right. Very good. Now let's go to the next one. Now the real deal starts here when you got to learn about phase and phase difference. Phase basically means position in terms of angle. So what I mean by that is when you go like in a circle and you complete the circle from one point, so let's suppose you start with A, you go here and come back to A. The angle that you've moved is 360 degrees. So we can say that one oscillation on a circle is equivalent to 360 degrees. But in reality, the waves also oscillate and we can assign them angles. So the total oscillation of a wave is also 360 degrees. So quarter will be 90, 180 for half, 270 for three quarters, and 360 for a full oscillation. Is it clear, kids? Yes. Write it down, please. Now, this relationship can be extended to other things. Like, for instance, if I draw wave like this, let's copy this wave, put it here and here. So at one time or at the same time, three things are happening. Not only the position is changing, but also the angle is changing and the time is changing, which means that if this is 0 degrees, this will be zero distance, this will be zero time. When it is at 90 degrees, at the same time, you will have basically a quarter lambda and a quarter time period covered up. Then at 180 degrees, you have half lambda and half time period. When it comes to 270, that is three quarters, so which means three quarter lambda and three quarter time period. A full 360 degrees will give us one lambda and one whole time period. Get it, kids? Now, because everything that you see on the screen is happening at the same time, so we can relate them with a symbol relationship. We can say 360 degrees is equivalent to a lambda and a time period. So this relationship you guys need to be aware of and always remember that because you will have to go back and forth between these three quantities when doing the questions. Okay, kids. Should I go forward, please? Everybody understands this? Okay. Now, let's check it out. So let's suppose we got to find phase of different points. All right. So can you guys one by one tell me the phase of A then? What do you guys say? Hurry up. 0 degrees. Okay. B, 90. C, very good, Fizzer and Asma. D, hurry up, everyone. Quickly. D is 270, no? Or 360. E, however, is 360. Very good. What about F? That's going to be 450. Very good. G, 540. H is 630. And I is 720. So phase means that particular position where they are at that moment. But then we can find the difference between 2 points, and we call that as phase difference. It basically comes out in angles. So between B and F, B is 90, F is 450. So what you're gonna do is you simply subtract it. So that means B is 90, so 450 minus 90 gives you 360 degrees. Whenever you have phase differences like 0, 360, 720, and so on, we call these points in phase. All right, kids, in phase. Similarly, if you find F and H, so F is 450, H is 630. Oh, let's write it like this. So that difference will be 180 degrees. And whenever you have a phase difference of like 180, 540, 900, and so on, that would be called anti-phase. Other than that, like you see D and E, so it's going to be 360 minus 270, that's 90 degrees. And that should be basically any other angle, like any other angle other than like multiples of 180 or 360. You call these points out of phase. So the three terms you're going to use. Okay, kids. Now, it's pretty simple. First thing about these points which are in phase, they will have the same direction. They will have the same speed. And they will have the same displacement. Then about this one, they will have opposite direction. These ones will have opposite velocity. And they will have opposite displacement because they're anti to each other. So exact opposite. When it comes to out of phase, they can have same or different direction depending on the points you're looking at. They will have different velocity. They will have different displacement. Like They will not be exactly opposite to each other, but they will be different from each other. Get it, kids? Please write this down, then I'll explain what they are and how to locate them on the graph. All right, kids, done. Should I go forward, please? All right. Now, please check this out. If you look at B and F, you might see that B is now, if I just wave, if I make a temporary like wave, that how it's going to move forward. So the next like iteration would be here, as you can see, which means that B is going to go down and F is also going to go down. They have the same displacement, same direction of travel, same speed. So that is why B and F are both in phase. Do you guys understand that? Okay. Uh, Asma, the wave, this black wave is going to move forward, right? You agree with that? Just look at like the dotted line I've made is like the next, like how it's going to move forward. It's just in future. Get it? So now think about it. Look at just point B. If the wave moves forward, point B has to travel downwards. Do you agree? So does the point F. It will also move downwards. Do you understand? Do they have the same direction of travel? Do they have the same displacement? So that means they're in phase. Do you get it? Right. Now, kids, look at the F and H. When F is going to go down, H is going to go up. Look at the dotted line where it is. You see F and H both have opposite displacements, where displacement is a vector quantity. They have the opposite velocity and they have the opposite direction of travel as well. So these are anti-phase to each other. Get it? Yes, Hajra, everything is clear. Alameen, Fiza, Shazib. Then the next kids. Think about it. Now, if you look at D and E, D is gonna go up. Fine. But E is going to go down. D has no velocity at this point. E has maximum velocity at this point. E will has zero displacement right now. D has maximum displacement. So they're just different. They're not opposite to each other. That is why D and E are out of phase. Is it clear, kids? Like that. Okay. Very, very nice. Okay. Should I go forward now? You guys? You can write this down. I will be just getting my tea and I will be back in 2 minutes, I believe. No, 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 no. All right, kids. So I'm back. Do they ask us to draw waves in which? Yes, they can do that. They can do that, Asma. And if they do, I will teach you everything. You just gotta wait. Okay? Let you know. You will see a lot of questions in this PDF about that. Anyway, so first of all, we are gonna work at this one. So it says a progressive radio wave has a vacuum, in a vacuum has a frequency of 75 megahertz. What is the phase difference between 2 points in the wave that are 50 centimeter apart from each other, and they are asking that in degrees? Okay, whenever this question comes, it's pretty easy to handle. Just remember, first of all, we got to find the time period or the wavelength. Okay, because we have learned previously that the degrees are related to lambda and time period with this relationship. So we're going to draw that relationship here. We know the frequencies here. I'm going to use 1 over 75 into 10 raised to 6 to find the time period. So then what you do, that's going to be, oh my God, that's a lot, you know? That's a lot. It's a lot of wave. Anyway, but the point is that, oh, wait. I cannot do this. I cannot do this. The reason I cannot do this because they're asking us in centimeters, so we have to find the lambda. Very clever there. So we have to use v is equal to f lambda first. Speed of light is 3.0 times 10 raised to 8. And the frequency is given as 75 into 10 raised to 6. And we've got to find the lambda first. So let's do that. So 3.0 into 10 raised to power 8 divided by 75 into 10 power 6. And I'm getting it as 4 meters. Interesting. All right. So 4 meters. 4 meters basically is equivalent to 400 centimeter, right? So I'm going to say if 360 degrees is equivalent to 400 centimeter, then what angle will be equivalent to 50 centimeter as this set? So they're basically apart. Cross multiply that. So it's going to be 360 times 50 divided by 400. Let's try this. And I'm getting the answer as 45 degrees, which is obviously answer B. Understood, you guys? If you have any questions, please let me know. Okay. If you have understood this, then I think you will be able to do the next question. Can you try that, please? Yes, kids. Any ideas about this? It says, what are the two next values of x where the displacement is y again? So you got to find the points that are in phase to this point and then look at the distance x there. B. Let's see. Anybody else? B. Okay, very good, Hajra. Very good, Asma. Come on, Alameen, Shazeb. Wake up, please. Furkan. Sleepers. Okay. If you ever get a question where you want to find the same displacement, you should take your ruler and just draw a horizontal line. Just draw that. Okay. When you draw a horizontal line, so it will give you this point. So you will have the same displacement at this point, and next time you will have same displacement is at this point. Obviously, the distance we got to go, the difference is lambda by 8. So lambda by 2 minus lambda by 8 will bring you backwards. So half minus 1 by 8 gives you 3 by 8. So this is 3 by 8 lambda, and this is lambda plus 1 by 8. So 1 plus 1 by 8 is 9 by 8. So let's look at what we have. 3 by 8, 9 by 8. B. Very good, kids. Excellent job. Very nice. Anyone who could not understand this, please let me know. Now, yes, Alameen, you want to find the same displacement. This is the displacement you got to find. So just draw a horizontal line to check which points it basically intersects with on the wave. Those points will have the same displacement as this one. Do you understand that point? Now, the difference, like this length, is equivalent to lambda by 8. So if I want to find a point before this, so the length I have to subtract from this is lambda by 8, which is 3 by 8. Do you get it? And in this one, because I got to go forward, so I have to add lambda by 8 to it to get that. Yes, very good. All right. Now, the next thing I'm going to go quickly forward before we will be able to draw some waves on our own. So we got to look at a term that is called wavefront, and wavefronts basically are perpendicular lines to direction of waves that connects with crests moving together. Which means is that these top parts are all crests. So if you draw a straight line, that would be a wavefront. Same goes here, wavefront. Same goes here, wavefront. Only crests are connected. These lines that you see are wavefronts, and the direction of wave is like this. So the wavefronts are always 90 degrees to the direction of wave. Just remember that. The other property that we should remember is that you can always find between two successive wavefronts, you can find lambda or time period depending on your need. All right. Now, all right, quickly write this down. All right, kids. Now, then comes the intensity of a wave. For intensity of a wave, just remember the definition of intensity is that it is power transmitted per unit area. The symbol for intensity is I, and the SI units of intensity are Newton per meter squared. Intensity is written as power over area, like that. But then sometimes we also like to write it as intensity equals to energy over time over area, because power is energy over time. That's why. Let's mark those. This is intensity, power, area. This is energy. This is time. So don't forget about that. Now, the real deal is here where intensity has certain relationships. So intensity basically is proportional to amplitude square, which basically means an increase of amplitude by 2 would increase the intensity by 4 because it is a function of square. Do you guys understand that? Similarly, for frequency, intensity is proportional to f square. So it's frequency square. If for frequency the intensity is I, so then for 2f frequency, intensity will be 4 times of that. However, the intensity is inversely proportional to distance square, and because of that, when intensity is I at a certain distance x, if you double that distance, intensity will be quarter now, because it will be reduced by 4 as x has a square on it. Now, to simplify it even more, I want you guys to learn these formulas. They are truly a lifesaver, and you don't need to think about the ratios. So yeah, sorry, the app crashed for some reason. I'm back. Sometimes on the iPad it crashes. All right. A1 square over A2 square, like that. In this one, intensity I1 over I2 will be equal to F1 square over F2 square, like that. So you got to remember these formulas, very important. For the last one, I1 over I2 will be equal to x2 square over x1 square. Why is that? Because it's an inverse relationship. An inverse relationship basically means 2 will be on top, 1 will be at the bottom, because it's a reciprocal there. All right, kids, will you be able to remember this? All right, quickly write this down so we can then move towards the questions. Very, very nice. Okay. Should I move forward, please? Sure. Right. All right, kids. So now this question basically is the same thing. Right now, it says that there are two waves, a wave X and wave Y, as you can see. And it says wave X has an amplitude A and frequency F. What is the frequency and what is the amplitude of Y? What do you guys say? Just by looking at it, it's fine. Quickly, please. This is pretty easy. B. Okay, let's check it out. So if this is A, the amplitude of the second wave is double of that. That's fine. Has to be 2A. These two cannot be true. And then A has one wave formed when half wave of Y is formed. So obviously the frequency of that is half as well. Very good, very good. That's correct. That's correct. All right. Now, kids, this was the easy part. Now let's go to the next. Okay. So this is the kind of question Asma was basically asking me, that when do we have to basically draw a wave? They have said that there is a wave, it's wave x passing at a point, and the intensity of wave x is I, as you can see. First of all, we got to determine the frequency. So can you help me out there, please? Hurry up, everyone. Take your calculators out. That's okay. One four, 1 4. No, 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 no. It's Asma, that's in milliseconds. It's not in seconds. You got to convert that. Yep, 250. Yes, Hajra, Fatma, why are you guys sleeping? Fiza, hurry up. Shazib, Furkan, don't sleep, please. Hurry up. Everybody should be doing this. So you guys need to basically find the time period. The time period is from this point to this point. That is 4 milliseconds. So 4 into 10 raised to minus 3 is the time period. Frequency will be 1 over 4 times 10 is minus 3. It should give you 250 hertz. Now, the real deal basically starts here, where it says a second wave z with same frequency as x also passes point B. Wave z has an intensity of 2I, and the phase difference between two waves are 90 degrees. So you got to draw that wave and label it as z. All right, kids? Now, first of all, we need to figure out that what will be the amplitude of that wave. We know that the formula is I1 over I2 equals to A1 square over A2 square. The intensity of the first wave was I, the second wave was 2I, the first wave amplitude is 2, as you can see. So I'm going to write 2 whole square. You don't need to make any conversions because this is a ratio. And we want to find the amplitude of the second wave. So I and I will cancel out. Uh, A2 will go there, 2 will go there. So A2 square equals to 2 times 2.0 whole square. Now just simply use the calculator to do it. So 2 times 2 square is 8 under root answer. So you're going to get A2 as 2.83 centimeters. Now, when you do that, you have the amplitude. Now we got to figure out what would be the phase. Now, as you can see, the time period in this one is 4 milliseconds. So I'm going to do it here as they need the working. So the time period is 4 millisecond, which is equivalent to 360 degrees. So what will be the difference of 90 degree in time? So I'm going to cross multiply that. So it's going to be 4 into 90 divided by 360. Let's do that. So if you check it out, it comes out to be just 1 millisecond. Now, what it means is that 1 millisecond means that I found this on. I didn't catch that. Could you try again? Okay, so 1 millisecond means every point. Why is there 360? Asma, one, like I said initially, 360 degrees is equivalent to a time period and is also equal to 1 lambda. Do you understand that? This is the relationship between these. So now please tell me what is the time period here. So that's why I'm saying this whole time period is equal to 360 degrees. They're all related like that. Get it? Because there is a phase difference of 90, so I'm going to find how much difference is there between the two waves with respect to time. So when I cross multiply this, I will get 1 millisecond difference. Understood? All right. Now this question is double trouble because we want to also adjust the lambda, sorry, the amplitude and the time. So every point will be 1 millisecond ahead of it. First of all, let's find it out. Remember, whenever you're doing these sort of questions, you got to take one point, most common points like the top ones, and this point for the new wave will shift 1 millisecond ahead, like that. It will go to 1. Get it, everyone? Any person who's confused about this point, please let me know. This one will move to 2. Everything is shifting forward, right? This 2 will move to 3. And this 3 will move to 4. And this 4 is going to move to 5, like that. Is it clear, kids? Now, the new the new amplitude was 2.8. So on the top point where the amplitude was, I'm going to find it is 2, 2.2, 2.4, 2.6, 2.8. Just above that, I'm going to put this point. Then this one is 0 amplitude, so it will be here. 2 was at negative, so it will be at 2.8 somewhere here. And then for the next one, which was 3, will be here, and 4 will be at 2.8, but at the top. So now let's draw this. Just make a smooth curve. Oh no, that's not fair. Like that. And this will be like this. So the new wave would look like this. Is that clear, kids? Why is it a straight line though? Like that. All right, kids. Any questions? Please let me know if you got confused at any point. Hajra, everything is clear? Asma, what about you? And Fatima, everything is clear? Shazib, Fiza? Furqan, what about you? Very good. Excellent, kids. So this is how you're going to draw this. Now there are pretty, like, I put so many questions about it. You guys need to do this one as homework. You also need to do the next one as homework. These are very similar questions. I'm sure you guys will be able to do. In any case, if you don't, do ask me so we can work on it. Anyhow, this is the last question I'm gonna do for you people, and this is a new one. Came like in 2022, so let's check it out. So in this one, it says parallel light sun incident normally on magnifying glass. The magnifying glass directs the light to an area A, and it has a radius of 5.5, as you can see on the diagram as well. Now it says the magnifying glass is circular and cross-sectional, has a radius this. The intensity of the light of the sun is 1.3. So here we have intensity I1 as 1.3. Then it says assume all the light incident on the magnifying is transmitted through it. Calculate the power of the light from the sun incident. So obviously intensity is given as power over area. Now intensity is 1.3. We got to find the power. Area is needs to be calculated actually. Now that's bad. So we have the radius. So we can use pi into 5.5 into 10 raised to minus 2. Why am I doing this? Because this is in centimeters. I'm going to convert into meters. So when you do this, I think you can check the answer, please. It should come out as 12.4 watts. Please check. All right. So, yeah. Then we're going to move to the next. It says the value of R, which is the distance here, is um, basically 1.5. So calculate the new intensity of this. Well, that's fine because we know that as the distance increase or decrease, there's basically a relationship between that, and that relationship is I1 over I2 equals to x2 square over x1 square. The initial intensity is 12.4, sorry, 1.3. The final intensity we got to find. Now, remember, x2 is basically, oh no, wait, oh no, x2, they want us to find what? Oh, this one. 1.5 whole square, and initially it is in millimeters. Oh, so clever. So we got to change that. Millimeter will be 10 raised to power minus 1 in centimeters. And then 5.5 whole square. Do you guys understand that? I have to basically make sure that the units are same. Okay, that's why I have to do this. It is in millimeters. I've converted into centimeters. When you do this, you should be getting somewhat like I2 as 1.75 into 10 raised to power 6 watt. You'll get it in kilowatts, basically 3 kilowatts. You can convert it into 1.75 into 10 raised to 6 watts. So this should be your answer then. Do you guys understand that? Yes, it is 1.75. I have basically the answer will be in kilowatts. So I converted at the end. You can convert in the start, that's fine. It's okay. That would work as well. All right, kids. Done, kids. Any questions here? Please let me know. All right, so make sure that you guys solve these questions for homework. You have a full week to complete it. You will get your tests checked by tomorrow morning, inshallah, and you'll receive the report. All right, see you then. Bye.